We're sitting in the heart of SAFIRE. And SAFIRE is based on the premise that the sun is a positively charged body in a generally negatively charged environment. The idea behind it is that electricity is the primal force in the universe. To do that, we create our sun, which is this anode, a positively charged body, in a generally negatively charged environment, which we get from these cathodes. And this is the chamber in which all the gases reside, and we watch quite phenomenal behavior, you might say. And have we been able to create the atmosphere of the sun? And the answer is yes, we have. And this is the main SAFIRE reactor. And on top we have a gimbal where we have probes to measure the plasma. We have antechamber, we have cameras, we have pumps, we have our main power supply, we've got resistors, we've got leak detectors, we have a large turbofan to cool the reactor down.
What about the little fan?
And we even have a little fan to cool the resistors. So think of the sun's atmosphere in this reactor, how hot it can get. It can get so hot, it will melt this stainless steel reactor. So we have to find a way to cool it down. And we have a turbofan here that will suck 14,000 cubic feet of air per minute at 2 inches of water. Think of a jet engine, and it would suck all the air out of this laboratory in about 2 minutes. So all that air gets moved inside this shroud that we have here, in between the shroud and the actual reactor, to cool the reactor surface down. So we can run the experiment for an unlimited amount of time.
Without melting.
Without melting.
Mississauga.
Mississauga. Without melting, Mississauga. Okay? And we need pumps. We need a lot of pumps. Pumps so we can get the inside of the reactor down to the vacuum that we see in space, or just off the surface of the sun. So we have roughing pumps, we have main pumps, we even have cryogenic pumps that freezes the gas or the atmosphere that's in there to bring it down even more. And beside that is a compressor that we use with helium. And the temperature is down to minus 275 degrees Celsius. And that's how we get the vacuum so low in the chamber. We have molecular pumps, we have roughing pumps, we have turbo pumps. We've got all kinds of pumps for all kinds of things. So that's a power supply. Now, with the sun, the idea behind it is that nature produces what's called DC power. It's flat. You've got AC power that comes to your house and it's alternating current. This is a DC power supply. And our calculations initially called for a 200 kilowatt power supply to get the energies that we see in SAFIRE. As it turns out, we need maybe a tenth of that. This section of the power supply is to control the power, and on the back side is where the main power comes from. This is a local control, and inside SAFCON we have what's called a remote control. So this is the back part of the power supply, where the main power is generated. We have large transformers, we have capacitors, we have resistors, cooling fans of course, and that's really about it. When it's on, you don't want to have your hands in here. This is a helium leak detector. We use this instrument to measure for any leaks that we might find in the chamber. When we're running a sun inside a reactor, things get hot and things can fail, and they do fail. When they do fail, we have to repair them, And we do repair them. We don't want any leaks to contaminate the atmosphere in there, so we know exactly what we have in the reactor when we're running the plasma. So we use this leak detector, and it tells us where the leak is. And right here we have oscilloscopes. And we use the oscilloscope to measure for radio frequency that we see in the plasma. We use it to measure the voltage and the current across the plasma. We also use it with the probes that you've seen as we take the probes down into the plasma, as we go through the double layers to look for electrical characteristics, as you'll see. Not bad. That's what it was. I knew it was some way. We did it and it worked for a while. And in this section of the reactor, there's a lot going on. We have a bolometer, which measures the total energy that's coming off of the core inside SAFIRE. We have radio frequency, like we have antennas on the inside of SAFIRE to measure for radio frequency. This is what we call the antechamber. And what the antechamber allows us to do is allows us to take the anode out from the main reactor, bring it back into this section here, close this valve, and then open up the chamber to change out the anode without contaminating the gas in the atmosphere that's in the reactor. This other section, well, there's just a lot going on here. Cooling systems to cool the core of SAFIRE. We have pressure sensors. We allow for gas to come in, evacuate this chamber here, and then put fresh gas back in preparation, once we close this again, to prepare the anode and the atmosphere that's in here to go back into the main reactor. And that way we don't contaminate the reactor. Okay, then we can take these things here, put them in the position here. And in this area of the reactor, we have a still camera, we have our gimbal, which controls the position of the probes, and it's a long hypodermic needle. Think of it in that way, that we can take into the plasma and move it around. We have ultraviolet light cameras, we have infrared cameras, we have video cameras, high definition cameras, we have thermal imaging as well. With the gimbal, as I mentioned before, we can move the gimbal around, which allows us to move the probe anywhere around in this region. Which allows us to bring the probe right up to the anode itself, measure through the plasma double layers to measure the electrical characteristics, the optical spectra, and the mass spectra. And that way we can tell what elements, what their energy states are, and what the electrical energies are. Maybe bring them in.
Needs a little bit of balancing too.
See what you can do.
Temperature stable.
And this is what we call our mass spectrometer table. What this does is it measures from 6 different regions within the chamber at any given time. We can measure the gas right at the anode or far away, and we can do comparative analysis of what elements are within the chamber in the gas at any given time, whether it's hydrogen or argon or nitrogen or helium or whatever it might be. It's a beautiful tool to tell us what's going on. Well, and underneath, these here are controllers for vacuum pumps for the mass spectrometer, and underneath is what we call our main SCADA data acquisition controllers. And what SCADA means is supervisory control and data acquisition. It's kind of a long name. But what it does is it collects all the data from all the sensors that we have on SAFIRE back into SAFCON on the computers so we can monitor the condition of the reactor at any given time.
And the yellow thing?
That's a plug. Talking about the cooling system, and these are the large Modine cooling fans. They're like a large radiator. Then beside that, we have a couple of tanks where we deionize water to take all the minerals out of the water. And from there, it goes into the main deionized water tank. Then it comes from there, goes into the main distribution pump and through the main manifold to all the different equipment that we have that needs to be cooled down, including the anode core and what we call the anode, well, it's a heat exchanger that's internal. You don't see it, but it's there. In any case, it's deionized water, and the unique thing about deionized water, it can be used as an electrical insulator. It doesn't collect electricity. And this is the variety of gases that we're running right now. This is compressed nitrogen, and this is what we use. It's very, very cold. We can compress. It's actually liquid nitrogen. And then when it comes out of the hoses, it turns into a gas, and that's what we feed the chamber with. Then we have, I think we have air, and we have, what do we have here? Maybe helium, and we have, let's say, sorry, I just turned my back to you. We have, this is hydrogen, no, this is argon, no, this is air. Then we have deuterium, you've heard about deuterium. And then we have hydrogen, high pressure and low pressure, and we have more hydrogen. We use a lot of hydrogen. And these gases go back from here, as you can see the lines, and they go back into the main control gas panel. Okay, as we mentioned before, if you saw before, we have the cathode on the other side of the door, actually at the back of the chamber as well. What this is here is, it's a ball screw, but it's control of the servo motor. And that allows us to bring the cathodes in closer or further apart. We got the patent on this design. It's an amazing thing because now we don't have to have any special equipment to try to ignite the plasma. We have full control over the cathode distance.
What about the duct?
The duct. Well, what my filmmaker calls the duct is that, you hear that sound? Well, that's just the servo motor here, if you listen to it, maintaining the cathode's position to within 0.01 millimeters.
And why is it quacking?
The reason why it's quacking is because I think the gain is set a little too high.
Okay. We're good.
You got that? Is that good?
Yeah, that's good. Perfect.
People have asked us, why would we have SAFIRE in a machine shop? Why do we rent this space? We worked out a deal with the company that owns this machine shop. SAFIRE actually is a very precision instrument. Those gimbals, hardware, the probes, and this is the inspection area. You have a CMM machine, or what's called a coordinate measuring machine. It measures very, very accurately with a ruby on the end. We have optical measurement. We have standards, just anything that you'd want to do with precision machining. And over in this section, what we have here, this is a real machine shop. This company makes precision parts for aerospace, for military, for nuclear reactors, and we thought it'd be just a great partnership. We have boring mills, we have lathes, we have standard mills, we have grinders, we have everything that we need to make all the parts we need for SAFIRE. And it's worked out. It's worked out perfectly. Cut.
So take us over to the...
Did you get all that? Is that good enough, or you want me to do it again? Do you want me to do it again without the buzzer?
No, that's good.
It's good?
We like the buzzer. Let's go.
We like the buzzer? Okay. It's a machine shop, yes, exactly. Except nobody's here today, so we can shoot. Okay. Ben doesn't like all the transformers buzzing and the machines going and they're grinding. You need to wear earmuffs, okay? You really do.
Okay.
So this is SAFCON. And it's what they call a sea container. And it works very well as a Faraday cage from any of the electromagnetic frequencies that we have going on in the reactor. Plus, as a Faraday cage, it protects all the computers that we have inside. And we have not just a few, we have a number of them. We've got to bring the pressure down and restabilize. So bring your pressure down and bring your power down. Your voltage back. Bring your power back, bring it back. Nitrogen flowing?
Yes.
Hydrogen flowing.
Yes.
So I view this.
Dang it. That's right. Okay, it's okay.
This is
Inspector's done. It's fine now.
okay. Let's bring it back up. What do you want? The 20 torque?
Yes, 2030.
Get it for 20.
2030 set.
Okay. Try to control your discharge here.
I'm supposed to vibrate where I want to be.
And now you're in SAFCON, and this is where it all happens. This is where we control the plasma. This is where we capture all the data. We have an IR camera, which measures the heat signature and temperature of the anode. We have a bolometer, as I said before. This is the screen that it produces to measure the total energy coming from SAFIRE. Obviously, we have the different plasmas, so that's what we use the video and still cameras for. And then off to the side, this is where the picoscope is, these 4 monitors right here. And this here, the signature where you see the red and the blue, that's actually what plasma looks like electrically as we're moving into the plasma. It has structure. It's like an electromagnetic force field. And it's a sphere, and you can't see it. You don't want to walk into it, but it's there. Then we have over here, we have UV, which is the black and white that tells us how much ultraviolet light we have, and we have a lot, and it's extremely high energy. Below that, we have the mass spectrometer, as I mentioned before, which measures all the elements in the periodic table and whatever elements we have in the reactor. Then off to that, we have what's called mass flow controllers. What they do is that if we want to introduce a precision mix of gases, let's say hydrogen or deuterium or nitrogen, and we want a very specific and accurate amount, we use these controllers to do that. Above that, we have pump control or vacuum control, where we can accurately hold the chamber at any given pressure that we want at any given time. And off over here to the side is where I was talking earlier about the SCADA. This screen here is where all that information, all the data acquisition on the pressures, the temperatures, the flow rates is captured in here, including the temperature of the reactor itself. And below that is where our main power supply control is. So we can govern exactly what kind of voltage and or current we allow to go into the chamber. And up here we have 2 large monitors. One where we're capturing 4K high resolution imagery in real-time feed, which is where you see all the beautiful pictures we're producing. And on the other monitor, we have a still camera. It's wide angle, and it shows where the cathode is and where the probes are, so we don't basically smash the probes into the anode.
Firm believer in picture is worth 1,000 words.
This is where we control the pumps and the main cooling system and what we call hydrogen diffusion, where we introduce nitrogen into the gas, the cooling system. What we have here is the deionization, so we can monitor the resistivity of the water to make sure that in fact the resistance is high enough that we're not going to be conducting electricity through into the anode. And what's interesting about this and what's important about this is that when we're pumping hydrogen, well, it's not like anything bad could ever happen when you're heating hydrogen up to, let's say, 80,000 degree electron temperature, and then you introduce that into the atmosphere, okay? We'd like to be in the news, but we don't want to be in the news because we've left a black hole in the middle of Mississauga someplace. So we introduce nitrogen in there to diffuse the hydrogen gas below explosive levels. We have a big red e-stop button right here, okay? Just in the event that something gets out of control. And then it just basically blasts nitrogen into the chamber, into the exhaust, and it's basically it's safe. It's a safe shutdown. It's an emergency shutdown procedure. And this is the main gas and vacuum control center. What we have here is we have both high and low vacuum. Now it's kind of inverse. When we think of high vacuum, you might think of higher pressure, but it's the opposite. High vacuum means it's really high vacuum. In here we have gate valve control. So if we want to bring a probe back, isolate it, we can close a gate valve. We have each valve for the mass spectroscopy, the mass spectrometer, you might say. That's where the 6 regions were I was talking about earlier. We can control each one of those from right here. This is the main power supply, the remote one that I was talking about, so we can control the main power supply from right here. And over here, we have gas and vacuum control for the gimbal, for the antechamber, to introduce gas as well as vacuum. Or you might say, we're not going to introduce vacuum, we're going to create vacuum and we can introduce gas. The center section of the control panel controls what's going on with the anode. And with this patented design, we introduce hydrogen into the core of the anode. That gas will diffuse through the anode, separating H2 to H, which is atomic hydrogen, and then it strips the electron off where we have free protons just at the surface. It's very cool. We can do the same thing with deuterium. And then over in this section here of the control panel is where we control the gas and the vacuum for the chamber itself. This is where we control the gimbal motion. We call it telemetry.
Okay, 865.73.
We have 2 monitors that allow us to see where the probes are situated in the chamber.
860.
We use servo motors to move the probes around
850.
in near the anode or out toward the double layers.
840.
We control the servo motors using keyboards and software. The gimbals can move the probes to within 0.01 millimeters of anywhere we want.
What are your X, Y, and Z for this? And I think you're going to back that off to 897.5 and see what happens. Yeah. Okay, good. Sounds good. Z, which is really B.
Yes.
This is one of my favorite instruments. This is called optical spectroscopy, and the technology dates back as far as Newton, from what we know. We took a prism and put light through it, and it splayed it out in that beautiful rainbow color. What we've learned since then is that every element has a unique light signature when it gets excited. So we know what hydrogen in it has a very specific, you might say, elemental DNA in a way. So when we do this, we bring the light in from SAFIRE through these fiber optics, through the probes. The light gets splayed out, the camera at the back captures it, and then it converts it into a signal that we see on the screen here. And I can tell you, this is sodium. This is hydrogen. This is argon. The cool thing about this technology is that it is extremely precise, zooming down to 0.0001 nanometers. That's a trillionth of a meter. So imagine looking at a meter stick and then stretching it out 1 trillion times. That's what we're doing with the light, and that is what's so amazing about optical spectroscopy.
And then we've got 486, 427, and 391. So 1 is looking line of sight.
Yes.
3 is looking just off the surface of the anode. Okay. And 4 is looking out further. 3
is close. 4.
The SAFIRE technology was designed and built to replicate the atmosphere of the Sun in a laboratory on Earth, and to test the electric sun model. These are the factors we control. These are some of the things the SAFIRE lab is now capable of. These are some of our recent discoveries. In our tests and experiments, we have found no disparities with the electric sun model. In fact, all the evidence to date indicates that electricity is the primal force in the universe.